Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good. So did anybody figure out why this works? What did you do over the break? Like have a good time or something? So the critical property is that if some process delivers n, then all correct processes must deliver n. So why is that true here? Yes?
If a correct process receives a message, but if a deliver is invoked on a correct process, it will eventually send it to all processes.
That's right. Invokes it here and then it sends it to all processes.
If the process is correct, then the abstraction anyway guarantees that a message sent from a correct process to another correct process will eventually be.
That's right. Virtual singly, if this process is correct, which that's the property. If some correct process delivers in, this process is correct, it will send a message, and so all correct processes will deliver in by that abstraction. Oh, here. Say again?
That's the reason nobody worked on this problem over the break.
Oh, because I already knew?
No, because they didn't have that.
Oh, I did. Well, that's right. Okay, so of course that's a very expensive way of implementing reliable broadcasts, and every time you receive a message, you're going to start echoing it to everybody else. It suddenly becomes very expensive. So you can do a simple optimization here, which is whenever you broadcast a message, you just broadcast it. You send a copy to every process in the view, and then you using simple basically vector timestamps, you piggyback a little bit of extra information on messages, saying like which messages you have delivered. Like I delivered the 5th message from process 1 and the 4th message from process 2, like a vector timestamp like we saw this morning. And then only at the end of the view, processes look at these vector timestamps that they've received from all the various processes, figure out if some messages may not have been received by everybody, and only then echo the messages that it doesn't know for sure have been delivered everywhere. So this whole three-way handshake at the end of the view is often crucial for building efficient algorithms. Like when you receive the stop view, you don't yield right away because you may still have to send some messages. So you receive a stop view, and you look at all the control information that you've received, figure something out about the state of the system, and then you still can send some messages, like the ones that you don't know have been delivered everywhere. Then you yield the view, and then you wait for the new view to be delivered. That's how you implement these things efficiently. So that's often the trick to making these protocols actually pretty efficient. So it's not every time you deliver a message you broadcast it to everybody else. That's only in fairly exceptional cases. Okay, let me talk a little bit about how you do replication in virtual synchrony. Must be said that virtual synchronous systems usually have built-in support for replication, but this is how one might implement it. I'll call this passive replication. It's like primary backup replication. There's some process that's the leader, which is the one with the minimum identifier, and clients send their operations to the leader. So the leader, when it gets a new operation from some client, sorry, what is this? Oh yeah, on new op. Okay, this is a little different than I remembered it to be. But when some process, a replica gets an operation from a client, it forwards it to the leader. The leader, that's here, that's Q in this case, when it receives one of these updates, computes the next state and the output, and then reliably broadcasts a message with the new state in it. Also keep track of a version number. Then it waits for acknowledgments from all the processes in the view. And when it has acknowledgments from all processes, not from a quorum, all processes in the view, then it sends the result back to the client. Yes. Yeah, I'm also confused, so go ahead.
So when you say for all Q in V, you mean you either wait for an ask or from faulty to tell you that somebody's faulty, because if you wait for everybody, you're dead.
I mean, this is really for all R and V because it's not the same Q.
Of course.
But, of course.
But right, you can't really wait for everyone. Or because somebody.
Well, so if how do I do that? So if you don't get an egg from everybody, then that operation will never be applied. It gets lost, but that's okay. We're only trying to make the system consistent, not necessarily. So there's something that maybe I should go into. Well, why the heck? Why not? I mean, there's the end-to-end argument, right? So the problem is the client has to retransmit in any case to the servers until it gets back a response. And so it's okay to drop the occasional request. It's not a big deal. So it is okay. So for example, if some processes in V have crashed and don't send an acknowledgement, nothing happens. That's fine.
Okay.
It will happen at the next view.
I was just thinking that since you have an accurate failure detector,
Right.
you could use it.
I could, but I only use that inside the implementation of the abstraction. The processes only see views. Okay, so that's when the leader finds out about. So Q is the client here. If you get an update operation, the primary executes. The leader executes that operation, sends a result to the client when it has received all acknowledgments.
So why do you have to wait for all the acknowledgements? I mean, we can work with quorum too.
But that's not this particular protocol. There are lots of protocols one could use, but in primary backup, you wait for an acknowledgement from all backups, not from a quorum. Certainly, we can go into protocols that use quorums and that have all kinds of other nice properties, but this is pure primary backup.
Once we have got one acknowledgement, I mean, we are pretty much sure of getting. What is the need of waiting for all? I mean, I think that.
Let me go into that when I finish describing this algorithm.
So I have a quick question. So you could wait permanently for the act, as you said,
Mm-hmm.
and the client will retransmit.
That's right.
What is the semantics of? You will get a new op,
Yes.
and you'll apply it on what state?
Well, so this would not. So because of this end-to-end argument, because of this retransmission necessity, an operation may be executed more than once. So we either have to assume, from the client's point of view, that operations are idempotent, doesn't matter, or we need to keep track in the state of what operations we've already executed, and it has to be treated as a no-op if it has already been executed. One of the two. And that's just because of the whole end-to-end issue, which hopefully somebody during this lecture series will go into. Okay, and this is executed by the backups. When you receive from the leader a new state, I haven't said anything about ordering. In fact, messages by these reliable broadcasts can be delivered in any order. So it has to do a little checking to make sure that it is a new state. So they keep track of a version number. If it's higher than the version number, they already know about that. They update their state, adjust the version number, and then send an acknowledgement back to the leader. But all it is really is, there's a leader, clients send their messages to the leader, and the leader then broadcasts to the backups and waits for acknowledgments. That's the basic idea. And so an important property, let me see what's on the next slide. No, I don't want to go there. An important property of this protocol to go starting addressing your question, is that a result is only sent to the client if all processes have updated the state, all of them. Otherwise, the client will not see a result. It's, by the client having received the result, it's guaranteed that all backups have it. And so if we at some point go to a new view and some new process becomes the leader, that leader is guaranteed to have executed the client operation. Now, if we had to use quorums, that would not be the case. Because in quorums, some processes may not have executed the operation. We have a new view, and the next view there's a new leader. That new leader may not have executed the client operation. And so the first thing that would happen in such a protocol is that the new leader first has to figure out what the heck is going on. And that means that it will have to ask a quorum of processes of the old view whether, like what the state is. And the problem, of course, is those processes in the old view may no longer be there. So it really complicates things quite a bit, and a little beyond where I wanted to go with this here. This certainly will come up in the PEXIS discussion. But in PEXIS, of course, there's only one set of processes. It's not dynamic like this. Yes? A bunch of questions. Good. How about you?
It's a reliable broadcast. It will eventually reach all the other participants of the view.
That's correct. All correct processes. Yeah.
So before changing the view, it will reach to all the participants. So as he pointed that, why should we wait? Because it will eventually reach before the view changes. So even the new leader will have that perform that particular operation.
That's a good point, actually. So the point is raised is because the view synchrony property, virtual synchrony property, guarantees that all correct processes deliver this update operation, and they all will execute it. Even if it hadn't sent an acknowledgement, it will still execute it before the next view starts. And so if it becomes the leader of the next view, it has the right state. It's a very good observation. There's one caveat, which is that the leader of the next view is not necessarily a process of the old view. So it could be a process that newly joined, in which case it doesn't have the state at all.
Even if the leaders are failed, and because the quorum
Yeah.
fails, it can ask, as you say, to everybody for the state,
Right.
and it can broadcast to the same newer one, or if it himself has
Yeah.
not executed that state, then it can.
No, I completely agree. So this is a very smart audience. I should have prepared for that better. But you're absolutely right. So so I think you're right. It's not actually necessary. So the quorum-based version, I think, might actually work. You have to, in any case, in the new view, if you have joining members or processes that may not be joining, but are in fact weren't in the quorum that were initially consulted. Well, actually, that's not a problem. If it's a new member, it has to get the state from the old processes in any case. So yeah, it's a very good solution. I hadn't thought of that. Might actually work just fine, unless I'm missing something, Lorenzo or Rebecca. I think it will work. Yeah, good point. Good point.
One of the issues might just be when you have the number of processes that are participating is changing, then the notion of majority is also changing.
Yeah, but it doesn't matter. I mean, so the quorums are only counted within a view. Let's see, it still seems to be a problem, though. What I'm worried about is because the virtual synchrony does not necessarily make the assumption that any set of processes survive into the next view. And so, I mean, at least one clearly, and so the problem is that entire quorum may be gone. And I think I think so. It still doesn't. No, I guess it doesn't work. You have to wait for all processes to Yeah, for all processes.
Client can send to all the processes.
Yeah.
Why only to leader? For example, if the leader fails, then if it is sending to all the processes.
Well, the leader is the one who keeps the leader is the one that keeps the primary version of the state. It applies the client operations in a particular order. Yes, clients can send to any replica, but all the replicas forwarded to the leader. If each replica would just on its own update the state, we would certainly get inconsistency.
But the assumption that leader is always active, it is not failing. If it fails, then if the leader fails, then basically this model will not work.
Well, if the leader fails, all the processes that survive into the next view, and there's at least one of them, and it's an assumption I haven't really stated, but at least one process needs to survive. If all of them crash, then there is no more view. That's the end of that. But so any process that survives into the next view has the state. That's why we're waiting for all processes to acknowledge.
But there is a difference between the family and other processes, because family is having more information than the other processes.
It doesn't really matter, though. All processes have enough information.
All are identical.
Yeah, I think what your point is that it might be the case that the primary received some updates that it then broadcast, or maybe didn't broadcast. It may have received them and may have ordered them. Those are going to get lost if the primary crashes and no correct process has delivered them. And then we're going to rely on the client retransmitting until it receives a result. This is something the client needs to do in any case, because its request to the replicas may have gotten lost. The only way it can deal with that is by retransmitting until it receives a result. So this was a very interesting discussion. But yeah, the quorum-based protocol, I don't for a second you guys had convinced me, but I don't think it will work unless you add some kind of assumption that a majority of the previous view survives into the next view. Then I think it can be done. But that is an additional assumption that, in fact, some group communication systems make. In fact, the way ISIS guaranteed that there was a unique sequence of views is by exactly that property. It wanted to guarantee, or it guarantees that a majority of the previous view makes it into the next view.
And here you are what is your only requirement?
I will go into that in a second, but I'm assuming consensus of some sort.
So I'm slightly confused. When the view changes and the new leader is not part of the old view, he has to get the state from.
He will have to get the state
right?
from some of the old members.
Right.
So he starts with a broadcast. Somebody send me the state, please.
So then why not just do the reliable broadcast and just return? Why even wait for the caller?
Sorry. Oh, why wait for the caller?
Yeah.
Sorry.
That's
So
one at all, because if that is executed correctly, then on deliver is
broadcast and then send the output back to the client.
That's right.
Because if the leader crashes right after that,
No,
the reliable broadcast only guarantees that the message is delivered if the sender is correct. But in this case, the sender is faulty. So if it was the case that even if the process is faulty, it would be reliably delivered, then you're right. There would be, in fact, no way for that message to get lost. However, to implement that, that would be a very expensive protocol.
So we can do one more thing, like we wait for the quorum, and then we do the travel broadcast to all. In that case, because the only problem we have saved was in terms of when leader fails and the quorum also goes out.
You don't need the quorum, right? You need one act back.
We need to wait for the quorum number of acknowledgements.
So I'm going to stop this highly interesting discussion here. There's a very good point here. There are many different protocols that can achieve the same thing. However, in order to understand whether a protocol works or not, you do have to prove it correct. And it's easy to think like, oh, here's a little optimization. Let's just use quorums, and everything will just work. And often these little optimizations don't work. And there's like the slight, corner cases where these things don't work anymore. And you'll see that later with like the consensus protocols. These are extremely subtle little protocols. It's very tempting to make little optimizations. You have to make sure every time you make a small change to the protocol, see if all the invariants still hold that you were assuming, all that kind of good stuff. But yes, there's more than one protocol to do primary backup replication. Here's a different way of doing replication, which is called active replication, also the replicated state machine approach. So in passive replication, there's one process that maintains a state and does operations on the state, and whenever it changes its state, it broadcasts that state to the other processes. In active replication, all replicas maintain a copy of the state, and there's one process that, or in any case, the various replicas each apply the operation. So they each have a copy of the state machine. Like in passive replication, there's only one copy of the state machine. There's n copies of the state. Here there are n copies of the state machine. All processes apply operations. In order to ensure that they stay the same, they have to apply the same operations in the same order. And so that's the difference between active and passive replication. So again, we're going to use a leader, though, because we need somebody to order the operations. We can do that through a leader. Protocol's a little simpler, in fact. So when some replica receives an operation, it sends that update to the leader. When the leader receives the update, it sends a message that includes a sequence number. Initially 0 and increments the sequence number. And whenever that message is delivered, the accept message, every replica that receives that message updates its state, increments its sequence number, and sends a result to the client. So all replicas send a result to the client, and the client will just be happy with the first one. It's a little subtlety here, but I won't go into. But if somebody sees it, sure, I'll go into it. But the basic idea is that we're using the leader to order the operations, but not to update the state and send it to the other processes. So it only orders the operation, send it to all the processes. All the processes execute the operation and compute a new state and a new output. Right? Just to go back to the old one. Here it's the state that's being broadcast to all the processes. Arguably not a very scalable way of doing things. Here it's the operation that's broadcast to the other processes, along with the sequence number, because we need to, the reliable broadcast doesn't give you ordered delivery. It only gives you reliable delivery. Subtle difference. So that's the active replication approach. Yes?
So it seems like notationally, on deliver, exec, off,
yeah. You're right. And that's the subtlety that I was referring to. It's really pattern matching here. It has to, so it says you can only execute the operation if it matches the sequence number. I could have written a bunch of if and while statements in order to make that right, but this is a little simpler. Okay, so how does Vsync garbage collection work? Oh no, group communication. I was looking at garbage collection. What the heck was I thinking of? Group communication. Garbage collection. It is for me 6 o'clock in the morning or something like that, so forgive me. Okay, so how does it work? How's that implemented? We didn't say a whole lot about that. I just told you what the properties are. Told you, some slight hints on how it's working. And so there's sort of two important mechanisms there. One is the messaging protocol that ensures that when a message is delivered, all causally prior messages are delivered as well. And then there is a so-called flush protocol that has to do with changing views. Okay, so here's a simple message protocol that doesn't use vector timestamps and yet gives you causal ordering. It's extremely simple. sure Lorenzo you did this kind of stuff, right? So basically, whenever you send a message, you just stick on that message. You piggyback all the messages you've ever received, and that's the whole protocol. When you deliver a message, you just deliver everything that's on that message that needed to be delivered to that process. And so it's a very simple protocol that obviously gives you this property that whenever a message is delivered, all causally prior messages are delivered too, because hey, the message includes all the messages that are causally prior to it. It's a completely non-blocking protocol. And by the way, as long as you get these messages in all the causally prior messages, you might as well deliver them in that order too. So whenever you deliver a message, you first deliver all the messages that were causally prior to the message, and then you deliver the message. That's called causal delivery, not broadcast, sorry. And that, in fact, can be handy for some applications, as we'll see in a second. So there's a simple protocol, not very practical. Messages just explode in size as the system runs. So in order to do a better job, we will use some kind of vector timestamps. In fact, we're going to use something slightly more complicated, matrix timestamps, which will. So a matrix timestamp is something like this. There's here a view with 3 processes, P, Q, and R. And in one of these entries, it specifies, so for example, P sent 2 messages to Q. And Q sent 3 messages to R. Q sent apparently 2 messages to itself. Probably should have put zeros on this diagonal, but I guess I wasn't thinking at the time. So I probably wrote them in the night too. So that's a matrix timestamp. It completely captures how many messages each process sent to every other process. And instead of piggybacking these messages on each of causally prior messages, we're just going to piggyback the matrix timestamp on messages. Is this concept clear to everybody, what this thing is? So we're going to piggyback that. Every process maintains one of these things, and whenever it receives a matrix timestamp, it does something very similar to the notion of vector timestamps that we've seen before. Basically, when a process receives one of these matrix timestamps, say R receives one of these things from P. So R can now see, oh, look at that. I should have received 1 message from P, 3 messages from Q, and 5 messages from myself. I only got 1 message from Q, so I better wait with delivering this message until I receive the 2 missing messages from Q. Now we have a blocking protocol, but with the same guarantees. It basically, you wait until you've received all the messages you learned from through these matrix timestamps throughout our messages. Is that notion pretty clear? Why can't we just use vectors? So vector timestamps count the number of events that happen at a process. But they don't say anything about those events. So say that we only had a vector timestamp. So when R gets, instead of a matrix timestamp, it gets a vector timestamp. Then it can see, oh, wow, there's 5 events that happened at process P, 3 events that happened at process Q, and 6 events that happened at my own process. From that, it cannot really learn whether those events were messages that were sent to R or to anywhere else. And so, but R needs to know, right? In this case, it knows like, oh, wait a minute, it's here. I'm supposed to get 3 messages from Q. It needs to know that information in order to be able to wait for that. If it only knows, well, there were 5 events, it doesn't know how long to wait or what to wait for. So this gives you more information. Yeah, but the number of messages sent could be to any process, right? So Q could have sent, Q has 6 send events in this case, right? 1 to P, 2 to Q and 3 to R. So if R learned there were 6 send events, it cannot learn from that 3 of those events were messages sent to it. It only knows there's a total of 6, but that's not enough information. So this gives you the necessary information to implement the causal ordering. Now, most of these group communication systems don't support point-to-point messaging. They only support broadcast. And if you have only broadcast, then a vector timestamp is sufficient. And in fact, if you read the papers, they all talk about vector timestamps here and vector timestamps there. It's because they only support broadcast. There is no way for P to send a message just to Q. The only thing that a process can do is broadcast. And then you have to use filtering if you want to implement some kind of point-to-point mechanism. So it's a trade-off. If you only do broadcasts, you don't have to send a matrix. You only have to send a vector. But the cost that you pay is that if you want to do a point-to-point message, you have to broadcast it and then filter it out at all the places that don't need it.
So you use blocking here in the sense that when a message is received, you can't immediately deliver it.
You can't deliver it until you know that you got the causally prior messages. And right, because if you did deliver it at that point, but you didn't wait for the causally prior messages, you may never get them because of failures. And so this is in order to implement the abstraction that no messages get lost, and like you're simulating no messages get lost. So you better ensure that if a message is delivered, all causally prior messages are delivered as well. Doesn't necessarily have to happen in that order. You could first deliver the message and then the causally prior messages, but you might as well put them in the right order. That has other advantages. So far, so good?
So in that case, wouldn't it be sufficient to just deliver the last message by introducing some sequence number there? Because it means when any process is delivering that particular message, all the prior messages are already received by that person. So, I mean, can we avoid acknowledging every previous prior message?
So nothing is being acknowledged here.
I mean, by deliver, when a process is delivering, as we saw, it's
Yeah.
actually sending an acknowledgement to the sender.
Under the covers, yes, that's true. I'm not sure how you would exploit that, though, for this. I mean, let's take that offline. I have no good answer to that, but I don't think it's sufficient. It's I think you
Some sequence number would be required because otherwise you don't know which processes were delivered.
yeah. I mean, this covers, this represents all the sequence numbers, right, on all the channels. Like with 3 processes, there are 9 possible channels if you include the self channel. So these are, in fact, all the sequence numbers of all the messages captured there in one nice representation. But I think you need to keep track of all of them in order to implement this causal delivery. Okay, so the other thing that needs to happen is this so-called flush protocol. So when there's a failure, then there's this protocol that runs. So I have here, upon suspicion of a failure, let's for now just assume upon a failure. Some process is being reported as faulty, or some process wants to join. Processes then broadcast a flush request. They ask the other processes, let's do a view change. When you receive one of these flush requests, for the first one in the view, a stop view upcall is delivered. Then the process is still allowed to send until it calls yield. And let's see, yield, and then the yield call actually is going to wait for all the messages that it's sent to be acknowledged. So when all processes have called yield, all the correct processes have called yield. In fact, all messages from correct process have been delivered. And because of the previous protocol, the causal delivery, all causally prior messages will have been delivered as well. And then when all known cross passages have done the yield call, we can do the new view, start a new view. So this basically is the protocol that terminates the old view before the new view is started. It basically ensures that all messages that are outstanding in the system are reliably delivered in the previous view. So yield doesn't return so the yield doesn't end until all messages that were sent by this particular the process that invokes yield have been acknowledged to it. So that guarantees all its messages have been delivered, and the causal protocol that we saw before ensures that all causally prior messages have been delivered as well. So by the time all correct processes have called yield, we get this property that all messages have been delivered, and there are no more messages outstanding. Yes? Is there a question? Okay. So that's the protocol that's called at the end of the view change. Is that clear too? This is all implementation, right? So now who actually proposes this new view? Right? So here I said a new view can be proposed. Right? Is when some failure happens. Everybody. It doesn't really matter who does this flush request, and it could be more than one process. But who comes up with the new view? Well, somebody. Let's call it an oracle. So here's one way of implementing such an oracle. So this is really the cornerstone of virtual syncing to ensure that there's only one sequence of views. So since failure detection is accurate, there is in fact such a thing as the oldest live member that everybody can agree on. And, well, you don't even need to agree on it. The process who thinks that it is the oldest live member because it detected the failure of all the processes with lower identifiers, well, let me take a step back. So in ISIS and many other Vsync protocols, the processes are actually identified. When you join, you get a new identifier that's guaranteed to be bigger than the older ones. So you can talk about the oldest live members, but if you want to think about it, the one with the minimum process identifier, that's fine too. I'm going to call it the oldest live member. A process can, by looking at its failure notifications that are accurate, can know that it's the minimum one or the oldest one. I'm going to call that the coordinator. It proposes a new view and broadcasts it to the members of the view. So when you think, as a member of a process, that you're the oldest process left around, you propose a new view and broadcast it. Now you wait for acknowledgments or new failure notifications. Right? If the coordinator gets acknowledgments or failure notifications from the other processes of the view, at that point we consider it committed, and then we tell all the other processes, here's the new view, it's committed. That's simple enough. The only unfortunate thing is that the coordinator itself may crash during this protocol. So if the coordinator itself crashes, there's some other process that thinks it's the oldest member that survives. Now, it may or may not have received the view from the first coordinator. Right? So we now have the first coordinator that crashed, and there's a new coordinator. That new coordinator may or may not have received the view proposal from the old one. If it did receive the proposal from the old one, it just uses that as the proposal for the new view. It cannot come up with its own at that point. If not, it can come. It can pick any. It can propose any view that it wants. Now, why does it have to pick the one from the old coordinator? That's to ensure that there's not the possibility that two different views get decided. If by having the coordinator, this view only gets committed if it's acknowledged by all of them, by all correct members. And so if the new coordinator didn't receive the proposal from the first coordinator, it's guaranteed not to be committed. It cannot have been committed because it can only have been committed if the new coordinator acknowledged that view. So if it didn't, the new coordinator can propose anything because it's guaranteed that the first one was not committed. So that way we can ensure that there's at most one view that gets committed, and under the assumption that there's at least one process that survives, eventually some coordinator will succeed in finishing this protocol. Go ahead.
Is there some requirement of continuity between UV and UV1 and UV2? Do the membership have to intersect?
Yeah, I mean, so something that I said in, before, I didn't write on my slides, but something that I am assuming throughout is that there's at least one process that survives from one view into the next.
Something that, when we were discussing the quorum before, it seems that if you're, true, requiring that a majority survives is more demanding than requiring that one survives.
Yeah.
But you do have the assumption that somebody survives.
Right.
And he's just making the assumption a
little bit stronger.
Which
you have to draw the line somewhere, right?
Right. But all I wanted to say is that, in principle, you also have to go to the previous view and talk to the previous view.
Right.
Because,
that's correct.
So, in principle, it's true that in theory there is no difference between theory and practice, but in practice there is.
Well, I mean, so the reason you need at least one to survive from one view into the next is because if none of the processes survived, your state is gone, guaranteed. You only need one to survive, and so it's sort of, in some sense, the minimum that you need. You can make it stronger. I mean, you could say, well, I'm going to require all processes have to survive into the next view, and that would clearly be too strong. The quorum might be a nice trade-off and certainly there are implementations that have done that.
But I guess that when we were having this long discussion, and when I, for instance, was thinking that this, when you were asking that, does it work, and I personally thought it would work, is because I saw that you also have to go to the previous view somehow, and you go to it in a more limited fashion.
Right, because I know that there's one process that survives and has the state. But yeah, I mean, you could certainly make it into quorum, but it's not as simple. That protocol that I showed doesn't work with just the quorum. I'm sure you can make it work, but you have to make more assumptions. So in any case, this is in fact a consensus protocol, a very simple one, and it's so simple because we're assuming accurate failure detection. Without accurate failure detection, you would have to do something much more complicated, and people after me, will go into that. Yes?
Is it possible that more than one process becomes the coordinator?
Yeah, but only one at a time, right? Again, there's because of accurate failure detection, if a process thinks it is the oldest live member of a view, it is the oldest live member of a view because failure detection is accurate. So there's exactly one coordinator. The only thing that we don't know is whether that coordinator, whether its view was committed or not. And the protocol that I gave you ensures that there's at most one view that gets committed. It's actually both safe and live. It's fairly easy to show.
In this case, if two members are, since the beginning we started to observe, since beginning two members are there, then who will select the coordinator?
Sorry, run that by me again.
You're saying that the coordinator is the oldest member.
Yes.
And if two members are, since beginning, both of them are there in all the views.
Yeah.
Then in the current view, who will be the coordinator?
Yeah. I mean, so that's actually a property that ISIS gives you, is that the oldest member of the view is always a member that was in the previous view, which simplifies things a little bit. It's a useful, simplifying property. Okay, so if you don't have perfect failure detection, we could use consensus to agree on a unique sequence of views. There's a little more that needs to happen in the absence of perfect failure detection, because actually the other protocols actually also depended on it, particularly the reliable message delivery, which ensures that if some process delivers a message, all causally prior messages are delivered as well. I believe it can be done. In fact, and I wrote a paper with Dahlia and Ken on that. There's a tech report. So it can be done without perfect failure detection, but it's certainly a whole lot easier through these discussions to start with thinking about not so much that the system is synchronous, but that there is a failure detector that can accurately detect failures. That simplifies a lot of protocols and simplifies a lot of the thinking about these protocols. But, of course, we can't have accurate failure detection. You can still implement the same abstraction with the consensus protocol. Okay, so I haven't talked much about ordering, and I actually don't know what time it is. How much time do I have? Like 15 minutes left? That's probably about right. So I talked about what are basically liveness properties, a little bit discussed as safety properties actually in this view mechanism. I showed an abstraction that guarantees that messages are delivered. I didn't say much about ordering. And ordering does make things a little easier. So we have broadcast protocols. I mean, the simplest one is like best effort. I love that term for its meaninglessness. Best effort means you try to get it delivered to everybody. I never know. It's like, why would I care whether something is best effort or not? But that's the going term. Send it and forget. Send and pray. Then there is reliable, which I defined. That is, if the sender is correct or some correct process delivers the message, then all correct processes have delivered the message. Actually, I think it probably have definitions for all these things. Yes. No, never mind. Actually, here. There they are. So reliable is that one. FIFO is the next obvious one. Says, well, we might as well deliver messages from the same sender in the order that sender sent the messages. That often simplifies things a little bit in the implementation of these algorithms. And that can be implemented with a simple sequence number, which you kind of need in any case in order to implement the reliability. Because the reliability, messages are in fact identified by the sender and a sequence number. Well, hey, if you have that sequence number already, you might as well order them in the same way. Then there's causal broadcast, which says, well, it has to be FIFO, and the messages have to be delivered consistent with the happens before order. So when you deliver a message, you have to first deliver any messages that come causally before it.
You really don't need FIFO when you say causal, right?
That's right. I'm sort of strengthening the notion that everyone is stronger than the one above, but like basically causal gives you FIFO automatically.
That's something that you pointed out.
Yes. And in fact, probably Tomic could have been FIFO, but I don't know. You can. It's easier to think of this hierarchy as you get what you already had plus some more. So you get the FIFO property plus this, and then there's something called atomic broadcast or totally ordered broadcast, and that's pretty different from the notion of atomic or the various versions of atomic that we've heard about this morning. This is yet another notion of what atomic means, which is that the messages have to be delivered in the same order at each process. Atomic is one of these terms that we use in computer science for any time we can't think of another word. So, huh?
Make a best effort.
Yeah, make a best effort. Right. Okay, so how? So here's a FIFO ordering with an example of something that's not FIFO. Can be simply implemented with a sequence number. When you receive something out of order, you just wait with delivering it until you receive the earlier message. And so this red message, that is delivered here out of order. So this process here has to wait with delivering this black message until after it has delivered the red message in order to make it FIFO. Now for broadcast, there's also local delivery. I didn't show that. I mean, you can basically deliver a message immediately upon sending that's sufficient. You never have to wait with delivering locally. So here's an execution that's FIFO but not causal. I guess we saw examples of that before. So this message, comes causally, was sent causally before this message. And so in order to make it causally ordered, we have to delay delivery of this red message until after the black message is delivered. Again, local delivery can be done immediately. So it's pretty easy to implement with these matrix timestamps. And if all you do is broadcast, if there is no such thing as point-to-point message delivery, as I pointed out before, then you can just use a vector timestamp. Atomic order, that's a little trickier. So atomic order is this property that all messages have to be delivered in the same order at all processes. And so this process here, so you cannot locally deliver immediately as with these other processes. It actually has to wait with local delivery until, one of them will have to wait with local delivery until the other one is delivered. So, if you have this atomic broadcast, it becomes very easy to implement passive and active replication because all this nonsense with versions and sequence numbers, it becomes unnecessary. You can just broadcast in this order. So it's a very primitive that really simplifies these replication protocols. So it can be implemented with a sequencer or rotating token protocol. So here's one with a sequencer. Sequencer is a leader. One of the processes, the leader is the process, and basically what you do to implement this protocol in a virtually synchronous abstraction is that every message that you send, you first send to the leader, and then the leader sends them to the other processes in FIFO order. And that will give you total order. Is that clear? It's pretty obvious, right? Token is a lot more fun. These dashed messages is a token that there's like a little packet that gets sent around the processes. So you have some ordering among the processes, and you just send this token around in a ring. And in order to broadcast the message, you wait for the token to come by, and when you have the token, you broadcast, and then you pass the token on to the next one in the ring. And the claim here is that if your message delivery is in causal order, then you also get total order. And the reason for that is, well, for example, here there's this broadcast and that broadcast because the token basically puts a causal dependency on these broadcasts. This broadcast and that broadcast. These messages have to be delivered before those messages. And so that token is the reason it exists is in fact to establish a causal ordering between these processes, and then from the causal delivery you get the total ordering. That's not usually how it's implemented, though. The way it's usually implemented is that the token contains a sequence number that gets incremented every time a message is sent, and then the messages are just delivered in the order of the sequence number. It's probably an easier way to implement it, but since we already have the causal delivery, we might as well exploit it. Can this be? That causal order implies, well, I mean, we can certainly prove the correctness of this protocol. I mean, so basically you would have to prove that if one process, I don't know, we might, for example, use proof by contradiction, say, so assume there's two processes that deliver messages in opposite orders. And then we would show that there is a causal dependency between those two messages because of the token. You cannot send a message until you have the token. So clearly, one message must be causally before the other, and so we would have a violation of causal delivery at the process that didn't deliver those messages in that order, and that would complete the proof. So that's how one would prove it. Without causal, if we didn't have causal delivery, we wouldn't get this nice property, right? Because without the causal delivery, there's nothing that says that you couldn't deliver this message over here. This could be delivered at any time. It's the causal delivery that guarantees the total ordering. So you need the causal delivery, and you can prove that with the causal delivery, the protocol works. Is that clear? Or you look pensive. That can be a good sign or a bad sign. Okay, so that was actually the end, I guess, of and that's probably timing-wise not that bad. There's 5 minutes left. Is that right? Did I get that right? Good. So tomorrow I'm going to be talking about gossip protocols. And so that's a whole different story. And it's better not that I get into that in the last 5 minutes, but maybe there are some more questions about the material that I presented, or I can do a quick recap in order to make sure you get what you paid for.
So I have a high-level question. So
yes.
All these proofs of those protocols that he said, there are proofs, right?
Well, that's a very good question. So the problem is you can't prove anything if you don't have a specification.
Right.
And so it's hard to find the specification in the first place of virtual synchrony in particular. So there have been surveys of various properties that virtual synchrony gives, but certainly the early virtual synchrony papers. Actually, this is not just virtual synchrony. I mean, if you look at the old systems papers, like people didn't used to believe in specification, and they still don't. But but it certainly didn't get worse over time. It's been rampant, and so virtual synchrony, there's no good specification, and then the other thing that happens is that people show these protocols, and then sometimes they prove some properties of these protocols, but certainly they don't show that it satisfies some specification because there is no specification. Now, that's a little different for the broadcast protocols. There's certainly proofs for, like, the atomic broadcast protocol, this is usually under assumption that there's a fixed membership, and in some sense we have that. Every epoch has a fixed membership. There are various protocols that have been shown and have been proved correct. There's a rich literature, and also all the books that were mentioned this morning, like Nancy Lynch's book, will contain these specifications of ordered broadcast and proofs thereof.
And there is this, I don't know but there is this old chapter of a book that never quite was by Sam and Vassos that
yes.
talks about.
Oh, yeah, that is actually a very good paper to look up.
Yeah, it's an excellent.
Yeah, so what Lorenzo points out, let's see, I think it was in Centuek, Vassos Hatzilakos, and wasn't there a third author?
I think
maybe just the two of them. They wrote a survey paper of broadcast protocols. Actually, that hierarchy that I showed really came from there. They show a specification of the properties, and then they give implementations thereof. I think the full paper does have proofs of correctness of them as well. So, and that's available online. It's a very nice survey of broadcast protocols. Yes.
So for some protocols, is there a systematic way for going from an asynchronous protocol to a virtual synchronous protocol, or at least has that been studied?
How to take? Well, I mean, so the virtual synchrony property, I mean, by its very name, it's more the other way around. You can take a protocol that was intended for a synchronous system and fairly easily port it into a virtually synchronous environment. So the synchronous protocols tend to be a lot simpler, and you can, because you have sort of a simulated synchronous environment, you can do that. You wouldn't do the other way around, because if you have a protocol for an asynchronous system, why run it in this synchronous environment?
Well, so there's a protocol for an asynchronous system that doesn't tolerate reconfiguration. that doesn't tolerate.
Oh, I see. So you want to take a protocol that cannot do reconfigurations, and now you want to extend it so that it can be elastic or dynamic in some way. Yeah. So you should be able to run that protocol in an epoch, and then because of the properties of the flush protocol, it becomes, we basically put a nice end to the protocol at the end of the epoch.
Yeah, but you have to derive what has to happen in the yield and what has to happen in.
Right, and so that's a good point. So now it depends on what properties that asynchronous protocol is trying to provide. If that asynchronous protocol is an atomic broadcast protocol, you're fine, I think. So you just order everything in one view, and then you go, you flush it. I shouldn't wave my arms. It doesn't like that. Whenever I wave my hands, it gets angry. So so in one view, the protocol would order all the messages, and then you start a new view, and then that same protocol can be used to order the messages there. And by the properties of message delivery in the views, you would still have a total order. So for that kind of ordering, it would work just fine. But I'm sure there are other properties one could come up with, which are probably maybe not ordering properties, where it wouldn't work. And to give an example of that, say you had a protocol that eliminates duplicate delivery. It's a protocol that says, oh, when there's a message that has already been delivered, don't deliver it again. Well, in that case, it would work within one view, but it would probably be nothing that prevents the next view from delivering a message that was delivered in a prior view. And so a protocol like that wouldn't just work simply in a virtual synchronous environment. So there's some properties that would be where it would work, what it would work for, and then some properties that wouldn't get transferred that easily. Any more quick last questions? Good. I'll see you guys tomorrow and we'll gossip. Thank you.